Previously, we defined potential energy and used it to state the work energy theorem. Now here I'd like to take a look at what else we can use potential energy for. And one of the things that happens a lot of times in physics is that we can figure out what the potential energy function for some system is, and we can use that to figure out what the forces involved might be. And the idea comes from looking back at the definition. We said that the change in potential energy had to be equal to the negative of the work done by the conservative force. Well, that's equal to the integral of the force dotted with the displacement. So if we remember that integration and differentiation are inverse processes to each other, we can take this and we can rearrange it into a differential form. And what we get, I'll write it like this, and I'll explain what I mean with it in a moment. This s here is just a placeholder variable. It could be x, y, z, r, whatever makes sense. But, so if I want the r component, say if I want the x component of a force, I find minus du dx. If I want to find the r component, I find minus du dr. And very technically, if you know what a partial derivative is, it's more correct for me to be writing this as the negative of the partial derivative, but that doesn't matter for what we're doing here. So let's just take a quick example of this. So let's say that we didn't know that the force of a spring was minus kx, but we had experimentally measured that we could write the potential energy for a spring as 1/2 kx squared. And again, this is where x equals 0 at equilibrium, which is the version I'm going to use here. So if I wanted to know the force of the spring, that will be minus d dx of u of s, so that's minus d dx of 1/2 kx squared. Well, k is a constant, half's a constant, derivative of x squared is 2x. So 2x times a half is 1. We got that minus sign up front. So sure enough, we discovered that our force of a spring is, I should probably write SP here, is equal to minus kx, which we already knew. But this also allows us to think about things graphically. So for instance, if I make a plot of the potential energy for our spring as a function of x, it's going to be some sort of parabola. That looks terrible. It's going to be some sort of parabola. I tried. I'll cheat it a little bit by moving the x. There we go. That's about as good as it's going to get. There. So this is u of x is 1/2 kx squared, potential energy for a spring. So at some location, if I want to know, say at this point right here, we'll call that x. If I want to know the force, I can find the slope at that point right there, and then I would conclude that the force is equal to the negative of the slope at that point. So this will tell us what the force is trying to do. If I actually have a particle located here, I look here and I see, oh, the slope is positive, but the force would be negative of the slope. So that means that it would be feeling a force trying to push it over to the left. Similarly, if I were over here, if my object were located here on the number line, say, I go look at the corresponding point on my potential energy graph. I look here and say, oh, hey, the slope is negative, but the force is minus the slope, so it'd be positive. Now, positive force means that it would be pointing to the right. So this is what we mean by a restoring force, by the way. This point right here is the equilibrium position, it's called. And at the equilibrium position, the slope is 0. So if I have an object right there, it will feel no force acting on it at that location. But we can also find the equilibrium position by setting du dx, or y, z, r, whatever, to 0. Again, the little circle over the equal sign means I'm setting it equal. And then solve for x, y, z, r, whatever. So in this example here, I would be getting that this would be kx would be equal to 0. We're saying that equals 0. So we get that the equilibrium position is 0. Which, considering that we had set up our coordinate system around the equilibrium position, is incredibly unsurprising, but we've all got to start somewhere, right? But we can do more with this. For instance, we can go and think more generally about the motion of something by thinking about what our total mechanical energy is. So let's just draw a line right across here and say that this is our total mechanical energy for the system. Well, when we're right here, where the potential energy is 0, we would have a maximum of kinetic energy. As I get further out, I'll have less kinetic and more potential. Then by the time I'm right here, all of my energy is potential. And I can't go any further to the left in this example here, because if I did, my potential energy would be greater than my total mechanical energy, which, in order to keep the total mechanical energy a constant by conservation of energy, that would force the kinetic energy to go negative, which it can't do because it's 1/2 mv squared, and all those numbers are guaranteed to be positive. So what that means is that this is a point beyond, so this point right here is a point beyond which the particle cannot go. We call this the turning point. And why do we say it's a turning point? Well, let's say the object here was initially going to the left. As it goes to the left, its kinetic energy decreases, potential energy increases until we get to the turning point. But look, the slope here is negative, which means the force is positive. And so it's feeling a force to the right. That means it's just going to turn around and head back. And we can do exactly the same sort of argument right here to conclude that this is the turning point on the right. And so what we get is that the object will oscillate between these two positions. In fact, the fancy name for this particular one is a simple harmonic oscillator. But the point is that it's oscillating back and forth between the turning points. Now, sometimes potential energy functions that we find in nature will look a little more complicated. And so this leads us to have to think about different kinds of equilibrium. So let's just say we have some experimental data. We measured a potential energy as a function of distance for something. And what we got looked, say, something like that. All right. Now, this is certainly more complicated, but we can still say something about the motion. So first off, we can identify our points of equilibrium by being wherever the derivative is 0. So these 3 points here are all equilibrium points. So they're all equilibrium points, but notice that one of them is different from the other two. These two here, the curve holds water. This one here, it spills water. So in the language of derivatives, what we have for all of these points here is that du dx is equal to 0. But for this one here and this one here, the second derivative, d squared u dx squared, is positive. Same for that one. And here, d squared u dx squared is negative. So remember, the second derivative tells us the curvature at a point here, and a second derivative is positive if it holds water, and it's negative if it spills water. Well, let's think about what that means. So let's say, for instance, we had our total mechanical energy was exactly equal to this local minimum right here. I'll just draw that much. If that's the case, the object is just plain stuck right at our equilibrium position, and it can't move. All right. Now let's say, though, we add just a little bit of energy to the system. Maybe a photon strikes the electron in an atom or something like that. And so the energy is just a little higher. This would still be our equilibrium position, but now these would be the turning points. And we could see that the object in the immediate vicinity of the equilibrium point, here the slope is negative, giving me a positive force. Here the slope is positive, giving me a negative force. The forces on one side or the other are always trying to return it back to the equilibrium position. Same kind of thing happens down here. But now let's say I gave just a little bit of extra energy to this one. Well, we can see, at least in the immediate vicinity, that there's no intersection. If I go over here, the slope is positive, so the force is negative. And here, the slope is negative, so the force is positive. So it means that if I give it a little nudge from this position, I add just a little bit of energy, what it's going to want to do is run away and not come back. So that's what we call an point of unstable equilibrium. And these turn out to be points of stable equilibrium. By that, we just mean if you give it a small deflection off, will it try to return back to the equilibrium position, or will it run away from the equilibrium position? So this is officially an equilibrium position right here, but if you breathe on it, it'll run away. Now, if we further out this example, we'll see, though, that in this particular case, it will eventually, our motion will eventually do something. this turns out to be a turning point at this total mechanical energy. So is that. So the object will, in fact, oscillate across from x equals whatever to x equals whatever between the two turning points. However, the motion is going to be more complicated because we can see as we go along here, the potential energy is going down. That would mean the kinetic energy would have to increase there. And then I'd have to head back down, and then I'd have to go up, and then I'd have to head back down. So we would be picking up speed to the stable equilibrium point, slowing down as we get to the unstable equilibrium, picking up speed as we get to the stable equilibrium point here, and then slowing down, and then we turn around and head back. So faster, slower, and then reversed. And so we get, just by looking at the graph, we can get a very good qualitative idea of exactly what our motion looks like. Now, sometimes you can get situations where things will run away forever. So I'm going to just take a look at a typical potential energy function that is associated with an intermolecular bond. So this will be as a function of, well, we'll just say x, sure. So this is the separation between two nuclei in an atom. This is the potential energy as a function of that. A classic model that gets used by theoreticians doing a calculation is a thing called the Lennard-Jones potential, or the 612 potential. It looks something like this, where we hit an asymptotic limit here. So now what's going to happen here is that if your total mechanical energy is higher than this bit right here, this is what's called the dissociation limit. Dissociation limit. What will happen here is if my molecule is given too much energy, what will happen is no matter where it is initially, at most it will, the position, the two atoms will get closer together to a point, and they'll turn around. Here's my turning point. And then after that, it's always going to be feeling a force off to the right. And then after that, it's heading off to the right. And because it has more total mechanical energy than potential energy, the kinetic energy will never get off to zero, will never get down to zero. So even though we're over here, the force will be to the left. We're slowing down. We aren't slowing down fast enough. And so what will just happen is the molecule breaks apart. On the other hand, if the total mechanical energy is less than the dissociation limit, then what will happen is the intermolecular position, the intermolecular separation, will separate between these two turning points. Anyway, we could go ahead and use this to, say, find the force and to find the this equilibrium point right here. So it turns out that in this model, we say that the potential energy is 4 epsilon, which is just a number, sigma, which you interpret as being the molecular size, over r to the 12th power minus sigma over r to the 6th power, thus the 612 name. So anyway, we can go ahead and find the equilibrium position by saying that the equilibrium position is where du dx is equal to 0. All right. So we can go ahead and differentiate this out. probably be easier for the moment just to rewrite the potential as 4 epsilon sigma to the 12 r to the negative 12 minus 4 epsilon sigma to the 6 r to the negative 6, just make it easier to think about. So then du dx will be, well, let's see, drop down to negative 12 will be a negative, yes, this will be negative 48, 4 times negative 12, epsilon sigma to the 12 r to the negative 13. And then let's see, this will be minus, so minus of minus is going to give us a plus. 6 times 4 is 24. Epsilon sigma to the 6 r to the negative 7. And if you want the force that the molecule feels, although we usually don't care, the force, since it's minus du dx, it would just be plus 48 epsilon sigma to the 12 r to the negative 13 minus 24 epsilon sigma to the 6 r to the negative 7. All right. But we're trying to find the equilibrium position, so we'll set du dx to 0 here. All right. So we've got negative 48 epsilon sigma to the 12 r to the negative 13 plus 24 epsilon sigma to the 6 r to the negative 7. We're setting that equal to 0. All right, I can divide both sides through by epsilon. 0 divided by epsilon is just 0. I can divide both sides through by 24. So then that will give me negative 2. Now I can divide both sides through by sigma to the 6th. So this will actually give me negative 2 sigma to the 6 r to the negative 13 plus r to the negative 7 equals 0. R equals 0 is not going to be a solution, so we can multiply both sides through by r to the 7. So that gives me negative 2 sigma to the 6 r to the negative 6 plus 1 equals 0. So then, let's see here, that will give me, and we'll rewrite it like this, 2 sigma to the 6 over r to the 6 equals 1. So then r will be the 6th root of 2 sigma to the 6th, or we can write this as the r is the 6th root of 2 times sigma. So, all right, that's a bit of a dry example. And like I said, we interpret sigma. Sigma is an empirically found quantity in this model that you roughly associate with the particle size, but it tells you something about the stable equilibrium, which is the point of this. All right, so with that, in the next set of videos, we will transition over to another conserved quantity, namely momentum. So we'll catch you over there.